this result. This result has an interesting consequence because the Taylor series of the trigonometric polynomial converge to the S uniformly. Okay, we have a remark. Taylor series of S converge to S uniformly. Okay, this is a basic result in the theory of Taylor series, power series. Okay, because S is the linear combination of sine and cosine, the Taylor series or the power series of sine and cosine has a very good property. They are convergent. They converge uniformly in any finite interval. Okay, so as linear combination, the Taylor series of the trigonometric polynomial S converge to S uniformly, and the S is very close to our function, continuous function f. Therefore, the Taylor series also converge to f uniformly. So that is to say, for any epsilon positive, there is the polynomial P such that the L infinity norm, this can be considered as a measure of the distance from f and p less than epsilon. This is the Weierstrass approximation theorem. Any continuous function can be approximated uniformly using polynomial. Okay. We have obtained a very good result on uniformly convergence of Fourier series. Okay, that is, if f is piecewise differentiable, then the Fourier series of f converge to f uniformly. Okay, and as application of this result, we obtained the approximation uniformly by trigonometric polynomial. That is this corollary. And then we also have the Weierstrass approximation theorem. That is, continuous function f can be approximated by a sequence of polynomial. Okay, that is to say, f minus pi continuous. Then there exists a sequence of Pn polynomial such that Pn converge to f uniformly on minus pi. This means f minus Pn L infinity norm goes to 0. Okay. Now, as application of uniformly convergence, we will study the so-called Parseval identity. We know that in our introduction of this chapter, we know that if f is square integrable L2, then the Fourier coefficient satisfies the Parseval inequality. That is A0 square plus k from 1, ak square plus bk square will not greater than 1 over pi f square Okay, we have this Parseval inequality. But now we will prove that this is actually an equality. We'll prove that this is actually an equality. So to do this, we observe that set xn to be the span by the first 2n plus 1 functions in the orthogonal system. That is 1 over square root of 2 cosine x sine x cosine nx sine nx. This is a subspace of L2. So we observe that what's Sn? Sn is the linear combination of this 2n plus 1 function. And the coefficient of the linear combination are the Fourier coefficient of f. Okay, I repeat again. Sn is the partial sum of the Fourier series of f. Therefore, Sn is a linear combination of these 2n plus 1 base functions of xn. So, Sn is the projection of f. Of f1xn. It is easy to see that this is the case. Then we know that the trigonometric system is orthonormal. These 2n plus 1 functions, are orthonormal. That is, any two of them taking integral from minus pi to pi will equal to 1 or 0. Any different one, integral 0. Multiplication of any different one taking integral, you obtain 0. You square any one of them, integral, you obtain 1. This is what we call orthonormal. Okay. Now, because this is orthonormal, we have the following result: 1 over pi minus pi Sn square x dx. This equal a0 square plus k from 1 to n ak square plus bk square. You just expand because Sn is half of a0 plus k equal to 1 ak cosine kx plus bk sine kx. Then the left hand side is precisely the inner product of Sn, which is Sn. But Sn is the linear combination of systems of orthonormal, linear combination of the orthonormal system cosine kx sine kx and 1 over square root of 2. A0 minus over 2 can be considered as a0 and a number 1 over square root of 2, then square. Okay, so this will be the maybe I will write this by a0 1 over square root. I will write a0 over 2 in this form. Then this is the base vector, one of the vector in the orthonormal system. Okay, and the a0 over square root of 2 is the coefficient. Then, because Sn is the linear combination of 1 over square root of 2 cosine kx and sine kx, and that is an orthonormal system. So the inner product of Sn, which itself is the sum of the coefficient square. That is a0 over square root of 2 square. That is a0 square over 2 plus the other coefficients are ak, bk. So ak square plus bk square for k from 1 to n. That is our this equality. Okay, and also we also have 1 over pi minus pi s n x minus fx square. What's this? This is just the norm of f minus Sn square. Okay, the norm is the square root of the inner product which itself. Okay, so in our very beginning, we know that this is f. This is orthogonal. This is the projection of f on xn. Therefore, this is Sn. So f minus Sn is this vector. So this is also normal. By the Pythagoras theorem, we know that this equal the norm of f square minus the norm of Sn square. The norm of f square is minus pi f square x dx minus pi Sn square x dx. Okay, so we also have this result. So the Parseval identity. Parseval identity is an improvement of Bessel inequality. Bessel inequality, we only have this is inequality, but we, as I mentioned, we will prove that this is actually an equality. So the result is called Parseval identity. Okay, so compare this with this result, the Parseval identity. Maybe I will write it here. Parseval identity. Parseval identity says that a0 square plus k from 1 ak square plus bk square equal 1 over pi minus pi f square. This is the Parseval identity we will prove. Compare this result with this. You see, this part is the first line in this page. So when n goes to 0, the Parseval identity is equivalent to say that when n goes to infinity, this goes to 0. Because the Sn square integral is precisely the sum of a0 square over 2 plus k from 1 to n ak square plus bk square. But the Parseval identity is k from 1 to infinity. That is n goes to infinity. So you want to prove that this is equal, you need to prove that this goes to 0 as n goes to infinity. Because the integral of f square does not depend on a constant, but the integral of Sn square is the summation of the square of the Fourier coefficients. You look at the first line in this page. You see that when n goes to infinity, the Sn goes to this. Okay, so this is precisely our Parseval identity. Okay, so we have this conclusion that to prove Parseval identity, we need to prove that this goes to 0 as n goes to infinity. That is, the left hand side goes to 0. Okay, so from this analysis, we already have the following remark. To prove Parseval identity, we only need is surface 1 over pi Sn x minus fx square goes to 0.